So, I really suck at Snake. So I decided to spend my weekend teaching an AI to play Snake for me. I started off by recreating my own little version of Snake, with a 20 by 20 grid for the AI to train in. Then, I blessed the Snake with the gift of vision. As shown, the Snake has 8 sensors in each direction. Each sensor detects the distance from the head of the Snake to the wall, if there is food in that direction, or if its body is in that direction. This means, for each of the 8 directions, there are 3 sensors, resulting in a total of 24 sensors for the Snake to see its environment with. Each of these sensors will be individual inputs for the neural network, with an additional 4 inputs telling the Snake what direction it's currently moving in. I've coloured these inputs pink, and they are 1 hot encoded. If you don't know what 1 hot means, it just means that only one of these 4 inputs will ever be active at once. So if the Snake is moving right, only the moving right neuron will be active, and the other 3 will be inactive. This network has 2 hidden layers with 16 neurons each, and 4 output neurons for each direction the Snake can go in. The output with the highest activation will determine which direction the Snake goes in. To train the neural networks of the snakes, I'll be using a genetic algorithm, which is just pretty much the process of natural selection, just like in nature. First, 1000 snakes are created with random neural networks. These snakes will make up the first generation's population. These snakes will then play their individual games until all 1000 snakes die. Then, to determine which snake should reproduce and survive into the next generation, the fitness of each snake will be calculated. The fitness of a snake is just a value, measuring how well the snake performed in their game. The higher the fitness, the better. We will discuss how we will determine the performance of each snake in their generation shortly, as this fitness function essentially determines what the snake will aim to learn and get better at. So now, by using the fitness value of each snake, the population of snakes will be ranked based on their performance in their games. The top 10% performers from this generation will be immediately copied into the next generation. Then, from the current population, 2 parent snakes will be determined by roulette wheel selection, which just means that snakes with a high fitness have a higher probability of being chosen as parent compared to lower fitness snakes. This means that while mainly better performing snakes will be chosen, the lower performing snakes still have a chance of being chosen to create a more variety in the next generation. These 2 parent snakes will then cross over their neural networks and produce a child snake. Then the child and this mutated child will then move to the next generation. This process will repeat until the next generation has reached the desired population of 1000 snakes. Then this next generation will become the current generation, and the cycle repeats. Using this, hopefully, over many generations, the snakes will learn to play Snake. If you're curious about how the neural networks are crossed over and mutated, here are the 2 main functions I used. The crossover networks function simply iterates through each weight of the neural networks of the 2 parents and averages the weight between the parents, and assigns that new weight to the child's neural network. And for each of these weights, by a random probability determined by the mutation rate, mutate the weight of the child's network. Mutating the weight is simply adding a random value between -1 and 1 to the original value of the weight. After trial and error, this is the fitness function I settled on, evaluating the snake's performance. I decided on this fitness function as the fitness will continue increasing for every extra step the snake makes. This was to incentivize the snake to prolong its life and avoid death early on in the learning process. I have multiplied this by the score squared to incentivize the snake to eat the apples, as they will greatly boost the fitness of the snake. I chose to square it with the intention that later on, when the snake starts scoring really high in each game, that eating 1 more apple than previously is a large increase in performance, and not just a small step up. So hopefully, this would make the snakes keep aiming to score higher and higher each game. Now, I know what you're thinking. Can't the snakes just go in circles and rack up 3 points forever? Don't you worry, I already thought of that. At the start of the game, the snake is given a limit of 250 moves, with each apple it eats granting the snake 100 more moves. If it runs out of moves, the snake dies, so for the snake to continue living, it must keep eating apples. This will prevent the snake from cheating the game and spinning in circles. Now, for the fun part, actually training the snake. Here, I've added a visualization of the activations of the neural network, with the direction chosen by the neural network circled at the output. For the sake of easier viewing, I'm only showing the best performing snake from each generation, but keep in mind that 1,000 snakes are playing simultaneously. By generation 13, the snakes have begun to start seeking out the apples, but they aren't very good at avoiding the walls. Around the generation 60 mark, the snakes have gotten pretty good at just brushing up against the wall and turning around at the last second. They also seem to have adopted the strategy of moving to the left side of the board and travelling up and down the board towards the right edge of the board, sweeping up any apples in the process. Now, fast forwarding to the 200th generation, we can observe that the snake has fully embraced the looping up and down the board from left to right strategy. I guess the reason for this behavior is as the fitness function rewards the snake for taking more steps each game, the snakes have evolved to take the longest path possible between apples as to maximize their reward. Still, after 200 generations of evolution, the snake has only achieved a disappointing score of 28. So, overnight, I let the algorithm run until generation 1000. Here is the final result of 1,000 generations of evolution. After 1,000 generations, the snake managed to achieve a score of 118, ultimately losing by turning left into its own tail. In the future, I believe the snake is capable of scoring much higher if I was to further optimize the fitness function and the neural network's architecture. However, training the AI takes hours, even running the games at 100x real-time speed. So for now, I'm happy with what the AI has accomplished.